Okay, good morning. So let's start the class. So today we will talk about, we will describe a new kind of group called permutation group. So permutation group are a special group, such it is still a group. Okay, the objects are permutations. Okay, and then let me see, and then the operator is, so we have a binary operator, which means we perform successive permutation. Okay, so it's a composite permutation thing, and then we will also describe a theorem called Burnside's theorem. Is that okay? But before that, let's talk about what is the coolest thing that we are going to do today. Okay, so let's consider we have these kinds of objects. So let's say we have a triangle, and then with vertices A, B, and C. Each of the vertices can be colored in black or white. Okay, so this is one of the case of ABC. So altogether, there should be how many cases? There should be 8 cases, right? So we will have another A, B, C, which colors like this, or so we will maybe color this one, or we may be coloring this one. Is that okay? Or maybe we will have a case like we will be coloring these two, or we will have a case like we are coloring these two, or we have a case of coloring these two, and then there's a last case that we colored everything. Is that okay? So there could be 8 different cases that we have. Now we say that, okay, so this is all ABC. Now we say that, let's say we say that 2 configurations are the same if one can be obtained to the other by doing some rotation. Okay, so in that case, how many distinct configurations do we have? So if you count, then this is one of the case. Is that okay? And actually, these 3 will be considered as another case, right? And then these 3 will be considered as another case, and this is one more case. So all the So in that sense, we will say that we have only 4 distinct configurations. Now suppose that today I change the question a little bit. Let's say I can color each of the vertices by one of the 5 colors. So you can have white or black or green or yellow or red. So you have many colors. Okay, then in that case, how many distinct configurations do we have? Is there an easier way to calculate this rather than drawing out all the possible cases? Okay, so this is, if we know Burnside's theorem, then we can solve this quite easily. Okay, so this is what we are going to do today. Okay, now before that. So before we describe Burnside's theorem, we need to define what is meant by a permutation group. So first of all, what is a permutation? So a permutation, as we know, is a mapping from a set S to itself, such that 1 is mapped to 1. So it is a 1-to-1 correspondence. So for instance, suppose that we have a set A that contains A, B, C, D, these 4 elements. Okay, so if I mapped A to B, B to A, C to C, D to D, then this is a permutation. Is that okay? So we can describe this describe this mapping by using this thing, like A, B, C, D. It is like A is now mapped to B, B is now mapped to A, C is now mapped to C, and D is now mapped to D. Is that okay? Of course, the ordering of this one does not matter. You can also write it as, let's say, B, A, D, C. So B is now mapped to A is mapped to B, D is mapped to D, and C is mapped to C. So these two represent the same thing. Okay, this describes original object is what? And what is the target object it is mapped to? Is that okay? Okay. So this is a permutation. So we can use a symbol to represent it. For instance, let's call it pi 1. So pi permutation. So I use pi for it. Okay. Now we can define composite operations. Pi 1, O pi 2. We can define something like this. Suppose that we have two permutations. Let's define another permutation. Like pi 1 is like this. Is A, B, C, D. B, A, C, D. O, another one is A, B, C, D, A, C, B, D. And then what is the result? Okay. Now it is like function. Okay. So it's like compound function, composite function. So we do this first, and then we do that. Is that okay? So in that case, where is going? What is the result? Okay. So the result will be some permutation, right? So if it is a permutation, it is a permutation. Then the result should be a permutation. And then, so how do we get the result? So it is like A is now mapped to A by the first permutation pi 2, and then A goes to B. Is that okay? A goes to this A, and this A goes to B. So in that case, A will go to B. Is that okay? And then B goes to C, and then this C goes to C. So B will go to C. Does that make sense? Okay, so it is like a function. Function of A is like A, and then G of A is B. So G of F of A is like B. Okay, so let's do one more. C is mapped to B first, and then this B goes to A. So in that case, C will go to A. Is that okay? And then finally, so I don't need to C because it is going to be a permutation. So it is going to be D. D goes to D, and then D goes to D. So it is D. If you are clear about the operator, so you can call it a joint operator or one after the other operator. So if you are okay with this definition, could you please raise your hand? Okay, good. Good. Now, now suppose that we have something called big pi. Let's say big pi contains all the permutations of the elements A, B, C, D. And then let's say we have this operator join. Then this is going to be a group. This is going to be a group. So first of all, so why is it a group? Why is it a group? So first of all, it is a closed operation. This one is a closed operation. If you have a permutation and then you get this permutation and then you apply another permutation, the resultant should still be a permutation. Does that make sense? Okay. Now associative, we need to verify it by algebra. So we skip this. This can be done. Okay. So we need to show that for any pi 1, O, pi 2, O, pi 3, it is no matter you do pi 1, O, pi 2 first or you do pi 2, O, pi 3 first, you get the same result. Okay, so you can prove that it is associative. And then there should be something called an identity. So what is an identity in this case? What is an identity in this case? The permutation that maps each element to itself. Is that okay? A maps to A, B maps to B. So this is a permutation. So if you look at this, this is the identity. Each one maps to itself. In that case, when you apply the two operations, A goes to A and then A goes to B, you get B. B goes to B and then B goes to A, you get A. C goes to C and then C goes to C, you get C. And D goes to D, D goes to D, you get D. So after applying this to the right-hand side, you get the same thing. And similarly, after applying this to the left-hand side of any permutation, you get the same thing. So this is the identity. Is that okay? And then how about the inverse? So each one should have a unique inverse. What is the inverse? So inverse is easy. You just exchange the two rows. So what is the inverse of this one? The inverse of this one is easy. So you just exchange this. So you put A, B, C, D here, and then you put B, A, C, D. Okay? So A maps, so let's see, what is the result? So A maps to B, but then B maps back to A. So A maps to A. B goes to A goes to B, so B goes to B. C to C, C to C, C, D to D, D. So you get the identity there. Is that okay? So this is called a permutation group. Okay. But looking at all the permutations may be boring. So sometimes we will look at the subgroup of a permutation group. Okay, so let's see some example. What is? Okay. So what can be a subgroup? Okay. Okay. So of course, this is a general definition. So you can have any kinds of sets of elements here. You just have ABCD, or you can have other kinds of objects. And then for the Burnside theorem, we will define what are the objects for A, for B, for C, for D, and E for F, blah, blah, blah. Is that okay? Good. So let's see an example of a permutation subgroup. So a subgroup of a permutation. So let's look at this G that contains these elements. A, B, C, D, and then A, B, C, D, and then you have A, B, C, D, you have B, A, C, D, and then you have A, B, C, D, and then you have A, B, D, C. Okay, and then you have A, B, C, D, and then B, A, D, C. Eh? B, A, D, C. Is that okay? So this is, we claim that this is a subgroup. Okay, so how do we check whether it is a subgroup? How do we check? To do the fewest thing. So first of all, this subgroup is finite, right? And then all the elements and the operators are from the original group, permutation group pi. So to check whether it is a subgroup, we just need to check whether it is closed. Excuse me. Is that okay? If it is closed, then you know that the identity must be there, the inverse must be there, and also associative rule must also be okay. Is that okay? So this is the identity, right? So if this one multiply with this one, then you get this one, there. This one multiply with this one, there. This one multiply with this one, there. Is that okay? This one multiply with this one is there. This one multiply with this one, it is there. This one multiply with this one, it is there. Okay, so good. So this one is good. How about this one? Okay, and one more. This one multiply with this one is there. Okay. How about this one? This one multiply with itself, what should we get? Identity. Excellent. This is the identity. You just swap AB, right? You do 2 times, you swap AB and then AB again. So you get itself. So it's there. Okay? So this is the inverse of itself. Okay? And then this one multiply with this one, what will happen? So this one says you swap AB, right? This one says you swap CD. Okay? No matter you do this first or you do this first, that's the same. This will be the answer. Is that okay? Is that okay? And then how about this one multiplied with this one? This one says I swap AB and swap DC. And then this one says, oh, I'm going to swap AB back. So the resulting will be this one. Is that okay? Okay? And it turns out that this is also commutative, it looks like. It looks like it is commutative, abelian. Because for any two permutations here that you see, this one multiplied with this one is the same as this one multiplied with this one. Is that okay? Okay? It looks like so. Okay. In general, it is not abelian. Permutation in general is not abelian. Eh? Is it? Let me see. Yeah, it is not abelian in general. Okay. But for this case, it is. Okay. So we have what? So we have G, and then this operator is a subgroup of this pi and then this operator. Okay, that's it. Okay, now Burnside. Okay, so let me see what is Burnside. Oh, one more thing. Okay. Okay. Okay, so now we have this definition. Okay. Okay, so we define. Okay. So we have this definition. So we define whether two elements in a we define the concept of related. Okay, so suppose that we have a certain permutation subgroup, let G, and then this one be a permutation subgroup. Okay. Okay, for every two elements A and B in this G, if there exists a sequence of you don't need a sequence. If there exists some sorry, this is not in G. Okay. Okay, let me make it a little bit more careful. So GS. So if you still remember, a permutation group has elements. All of them are permutation of the items of a certain set. Okay, so let's say the set of items is S. Okay, so in the examples that we have, this S are the items A, B, C, D. Is that okay? And then this G of S contains what? G of S contains these four permutations of A, B, C, D. Is that okay? So my definition here is that we consider S in our example with A, B, C, D, and then we call this G of S instead of G. So to specify that the individual item in the permutation is from the set S. Is that okay? Okay. So we define a concept called related. Okay. So if there exists some permutation of G that maps A to B, then, so this is the definition. We say A and B are related. Is that okay? So let's denote this. Okay, so let's denote this. They are related. So maybe we will say A is related to B. So we use this to stand for related. Is that okay? Okay. Now, what is so special about this relationship? So all these are for the preparation to describe the Burnside theorem. So let's take a look. Okay, we have an example here. We have an example here. So here A is related to A because there is a permutation that maps A to A. Is that okay? A is related to B. Okay. And then C is related to C. C is related to D. Is that okay? Is that okay? Okay. And then we are claiming that. So this is the theorem. This relation is an equivalence relation. This relation is an equivalence relation. So what does that mean? Okay. So based on this thing, so the consequence is that based on this thing, we can partition the items in S into different groups. Each group, the items are all related to themselves. Is that okay? So we still need to have a proof for this one, and that is easy, okay? So any item A is related to itself. Reason? Because there is the identity permutation. Is that okay? Okay. Now if A is related to B, so let's say they are distinct items, then B must be related to A. Is that okay? Because it is a group. So if there is a permutation that maps A to B, the inverse will map B to A. Does that make sense? Okay? Good. So another, if A is related to B, B is related to C, then we will have A is related to C. That's easy. There is a permutation that maps A to B. And then after we apply this permutation, we apply the permutation that maps B to C. So A will be now mapped to C, right? And because this is a group, operators are closed. So there is a permutation pi that maps A to B. And then there is another permutation pi that maps B to C. Is that okay? So this will be a permutation pi that maps A to C, right? And then because it is closed, so the product of these two implies that the resulting thing must be in the group. Okay? So that means that there is a permutation in the group that maps A to C. So this is an equivalence class. Okay?